there. Almost there, though. All right, so I'm going to put a star on number 7 because this one's giving you points, but I'd like you to try to figure this one out first before I spoil the fun for you. It doesn't seem like it would follow the same kind of approach that we took, but really if you're thinking about the idea that we need something perpendicular to the plane that all of these 3 points are on, then you start kind of hopefully thinking along the lines of cross product, right? Because if you know the definition of cross product as, you know, it generates a vector that's perpendicular to 2 given vectors, then it seems like it's precisely what we need. Right? So if you create 2 vectors out of this and find the cross product, you'll get your normal vector, and then all you need is a point on the plane. Any one of these 3 would suffice, and off you go. All right, so cross product galore here. Intersection of planes. This could be easy or it could be pretty challenging. It depends on the way the question is phrased. So 2 planes in 3 dimensions are either parallel or they intersect in a straight line. All right, so they're parallel or they're not. So the relationship that exists for lines in 2 space does not apply to lines in 3 space, because you could have skew lines, you know, lines that they don't intersect and they're not parallel to one another. But the relationship for lines in 2 space does transfer over to planes in 3 space. Right? So that idea of they're either parallel or they're not, that is true for planes in 3 space. All right? So the question would become, well, all right, in what way would they intersect if they do intersect? Right? They could have a perpendicular relationship, or they could just be at a slant, you know, or maybe they're parallel completely. The good thing about it is if you can make a determination of the relationship between the normal vectors, then you'll have an idea of what the relationship is between the planes, right? Because, you know, my enemy of my enemy is my friend. It's that idea. If you're talking about the normal vectors being perpendicular to one another, right, the planes that originate those normal vectors must also be perpendicular to one another, right? So if the normal vectors are parallel to one another, then the planes themselves must be parallel to one another, right? So it's funny. So this is the easiest analogy, the pen between the fingers, but I can't not, like, I have a disturbed mind, I guess. It's like a nail right through the hand. There's my normal vector. You know, so, but that, I mean, this is obviously the safer way to go. Right? So if you have a pen in one hand and a pen in the other, you can easily see the relationship. Right? So they're both parallel to one another, so the planes would be parallel to one another. All right? They're perpendicular to one another, the planes are going to be perpendicular to one another. All right, and just imagine that being a bloody mess with nails, and you'll yeah. So you can Halloween costume ideas. You have one right there. You can be perpendicular vector, perpendicular planes. You know, so you know, just like with fake blood. You know, not terrifying.
Call the chainsaw vector.
Yeah, Texas chainsaw vector. Yeah. All right, so that's what all this is addressing. Okay, so we want to find the equation of a plane containing the point 3, 1, 4 that is parallel to the plane to, well, I was going to just name off the perpendicular vector 2, 1, 1, but that's really the key to understanding how to handle something like this. So if I know that the normal vector is going to be 2, 1, 1, and it's going to be parallel. So this point is not living in this plane, but it's a point that's parallel to that plane, which means that the normal vectors would be scalar multiples of one another. All right. So I can invent a new normal vector if I want. You know, double it, triple it, multiply it by -1, -1/2, doesn't make a difference. Or I could just use that. Right? Because the direction of it would have to be the same. Right? So this would be my x sub o, y sub o, z sub o. Now, these points would not satisfy this equation. And if I plug in a 3, 1, 4, here I'm not going to get 1 as a result. So what I need is a new d value to represent the plane that is parallel to this. All right, so my new plane is going to be 2x plus y plus z equals something other than 1. All right, so I'm going to find the dot product between n and x. Well, I'll just actually write it. I was going to use notation, but 2, 1, 1, and 3, 1, 4. It's going to give us 6 plus 1 plus 4 equals 11. And so therefore, we're looking at a plane 2x plus y plus z equals 11. All right. Now, personally, I don't know. You might feel differently about this. It's not. This is by no means a requirement, but I am pushing this GeoGebra stuff through the tech assignments. So you may think, well, I'll just do the GeoGebra to satisfy his weird need to have us use that software just for tech assignment purposes. But I'm never going to use it for anything other than that. That's fine. But I would like to know that I just did this correctly. So I put 2 planes in, make sure I type it in correctly in theory. All right, I did not because my planes don't look right. I'll get it up on the screen in a sec. I just want to make sure I have it in here correctly before I give it to you. I accidentally typed in 2x plus y plus x again. It was weird. It's a weird mistake to make. All right, so here we go. Got my 2 planes, the original, the extra crispy, and you put a little sphere in there and you have a TIE fighter. Yeah. This looks like the targeting scanners on the Millennium Falcon. All right, so, okay, cool. We know it's parallel, but we knew that before we tried figuring out the 11. All right, well, how do I really know it's right? Well, let me put the point that's supposed to be on my new plane. 3, 1, 4. That does appear to be on my new plane. All right, maybe you're not sure that that's the new plane, so let me shut off the one that was the old plane. All right, my new plane does contain the given point. I did it right. It's not even like I'm pretty sure I did it right. I did it right. They're parallel to one another, and the given point is on the plane that I wanted it to be on. All right, so GeoGebra is a really good resource to make sure you got a good handle on this stuff.
How is it that you said that at one point you feel like GeoGebra would be available during the test? How would you do that?
They have a test feature.
But then you would have a computer with you, or a tablet, or a phone?
Yeah, so the student would have to have a tablet that has the GeoGebra app on it. Then you would enable the testing feature on it. That locks you out of every other feature on the tablet, except for the functions on GeoGebra that I'm willing to allow, which is most of them. And then it has a set screen. So like the border on this one is blue. It would turn to green or red, I can't remember, but a different color than blue that lets me know that you're in test mode. If I set it up with, I think it's Apple Classroom, then I could actually see your screens on my laptop. And then after all that's over, let's say you figure out like, okay, that's cool. He didn't come around and look. He's not looking at his laptop. I could totally cheat. At the end, once you disable the testing feature, it tells you, or it tells me, the amount of uninterrupted time for which you were in the test mode. So if the test started at 6 o'clock and ended at 8 o'clock, and it says that you were only in uninterrupted test mode for 15 minutes, I'd make you sign a waiver beforehand that says that if anything like that happens, you're getting a 0, but that would mean that you were out of the testing mode, in which case you had access to the internet. And which, well, that's the reason why we don't do it already. Yeah, because I can't guarantee that
But
yet.
then we would be able to do something like this, where we could verify, oh, this is actually parallel. This is
Exactly.
awesome. I know I got this right.
Yeah, I mean, we're almost there. We're not there yet, but we're almost there. Like I think we're maybe like probably a year and a half away. So I don't know. I'd like to see it happen sooner rather than later, but
That doesn't help us very much.
I know. I know. But when you think about the fact that I had to learn all this crap without Google and stuff, and YouTube, and
No GeoGebra.
and TI-83s,
I had those.
I didn't even have that. Like that's like, so put that in perspective. Like we had, when I was starting out, it was TI-81s and then TI-85s, and then after that it was TI-83s. But half of the functionality was either not created on the TI-85 or none of my teachers knew how to use it, so they couldn't teach us how to use it. So it was like it didn't exist anyway. So I had nothing except for my wits and my will to survive. So anyway, process for finding intersection of planes, because that's not too bad. You're given a point, that the parallel vector, the normal vector is going to be parallel, so you can use the same vector. That's great. But what happens if they're going to intersect? You have to find the parametric equation of the line that represents the intersection between those two planes. Because if you imagine, and I can help you imagine in a few minutes, two planes intersecting, the path that's generated by that intersection will be a line. And we've already covered the fact that the only way you're going to represent a line in space is with parametric equations. So this technique is going to help us do that. All right, so it's elimination. Eliminate one variable from the two equations and solve the remaining equation for one of its variables in terms of the other, blah, 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 blah. All right, so what we can do, let me get a pen out here, do it in red. I'll work off of this, because I need to find the perpendicular vector, or the normal vector to the plane. I know that each of these vectors must exist on the same plane if all the points would be on the plane. So I can name these points however I want. So I'll call it PQR. So I need QP, and I would need QR. All right, so just subtraction. So 3 minus negative 1 would be 4. 1 minus negative 2 would be 3. And 4 minus negative 3 would be 7. All right, so just subtracting the corresponding parts. And I would do the same thing for Q to R. So 2 minus negative 1 would be 3. 7 minus negative 2 would be 9. And 1 minus negative 3 would be 4. All right. Now the technique that allows us to come up with a perpendicular vector to two given vectors would be the cross product. So I want the cross product of QP and QR. All right, so I'd write it as IJK 437 394. Really don't need the picture anymore, because the cross product is really all I need. Because in order to write the equation of a plane, we know that you need the normal vector and a point on the plane. And if you have those two pieces of information, you pretty much have what you need. All right, so what are we talking about? 12 minus 63, so negative 51. 7 times 9 is 63, right?
Yeah.
Okay. So negative 51i. Then for the j's, we're talking 16 minus 21, so that'd be negative 5, but it's already negative, so plus 5. And then for the k, 36 minus 9, which would be 27, so plus 27k. All right, I did all that way too quickly, so if you spot an error, let me know. I mean, you were planning on doing that anyway, but yeah. Sooner rather than later, because everything else is going to be based off of this. All right. So I'm just doing a quick mental double check. So we got 12 minus 63. I think that's negative 51. For the j, we had 16 minus 21, so negative 5. And then for the k, 36 minus 9, 26. I think, shockingly, I may be correct. It's possible. All right, so my normal vector is going to be negative 51, 5, 27. All right, so those are my A, B, and C values. You can label that if you want. All right, so we have the left-hand side of the plane equation. We just need the right-hand side. So for that, we pick a point out of the 3 that we're given, because it could work for any of the 3, because all 3 of those points fall on the plane. All right, so choose the one you like the most. They're all pretty gross, so I'll take the first one. I'm going to call that x sub o, y sub o, z sub o. All right, so to get the right-hand side, I want the dot product between that and my normal vector. All right, so we're looking at, you can call it D if you want. Well, wondering what D are you referring to? All right, so it would be, again, the dot product of the ABC and your selected point, in this case 3, 1, 4. All right, so that's negative 153 plus 5 plus 108. All right, so that's negative 153 plus 113. So that's negative 40. All right, so I'm not really 100% sure why I'm doing all of this in my head. It's dangerous. But the plane equation, assuming any of that was correct, the mental gymnastics, would be negative 51x plus 5y plus 27z equals negative 40. No. Of course, the one thing I do screw up on is drawing a line, because for some reason I can't do that. Try that again. Oh boy. Ooh, nerve-wracking. That's the definition. The cross product, the definition of a cross product is a vector that is orthogonal to 2 given vectors. All right, so we can verify this, because this should satisfy, any one of these points should satisfy the equation. So plug in the 2, 7, 1, hopefully it gives a negative 40.
If you did your vectors based on a different point, you would get like an equivalent plane, right? Just multiplied by a scalar?
Correct. Equivalent plane, possibly off by some scalar. And also possibly it could be exactly the same, but that's pretty rare. You know, it would be pretty convenient if you were able to select another point and get the exact same equation. You, in all likelihood, get a scalar multiple of what it is that you're going for. Right. So, you know, there's a little bit more teeth to a problem like this, but nothing you haven't seen before. The new component, of course, is the part where you actually make a plane equation out of it. All right. But yeah, like I said, you selected one point, select another point as a check. It doesn't matter which one you select, but just pop it in and make sure it gives you equivalence. I kind of don't want to out of fear that I'm wrong. I should do it, you know, just for clarity's sake. Let's see, negative 51 times 2 plus 5 times 7
Plus 27.
plus 27, right? Thank you. And you get a negative 40. So it does check out for at least the second point. So you can reasonably assume that the third point is going to work also. I'm going to show you a better way than that, though. So, linear algebra, our best friend when it comes to stuff like this. Because we can, if we want, solve by eliminating a variable. It looks like z would be a nice variable to eliminate here. You know, you subtract the two equations from each other, z would go away. So z would be your independent parameter, and from there you can figure out everything else. But let's not do it that way. All right, let us write a coefficient matrix 2, 1, 1, 1, 3, negative 5, 1, 4. And we're going to row reduce that. Put that in reduced row echelon form. R ref. All right, so to the calculus, to the Hindenpeter. Again, it's the linear algebra stuff is not me tooting my own horn or anything. It's like, oh, cool, I know linear algebra. It's not for that. It's supposed to be a gift for you. It's supposed to help you not have to do the mundane algebra that would take you minutes to do. All right, and I don't mean minutes like 1 or 2 minutes. I mean minutes like 10 or 15 minutes. All right, so in this case, it's not too bad, but sometimes it can get pretty out of hand. So the linear algebra just keeps you from getting bogged down in that. And also, I mean, you know how it is. You do the simple algebra, and you make the simple mistake in the simple algebra, and then you spend the next 10 minutes trying to figure out what the hell you did wrong. So this is going to help alleviate that. So you want to become very familiar with this because it is a time saver, and you know there's I don't even know. It's supposed to be a gift for you.
It's not viewable.
What's that?
It's not viewable, or at least not all the way through.
No.
Like I can't.
Hit math.
I got.
Isn't it 2 by 4?
Yeah, I got distracted.
2
And
by 4.
I was in motivational speech mode.
Thank you, buddy.
Yeah, we know we got storytelling mode, we got joke mode, we got the this'll serve you well, listen to me, I know the way mode. And then mix in there is like, and now I'll show you how to do this and that and the other thing. All right, so type in your entries, each coefficient in your system, and then quit out of there, go back into the matrix, go to math, find ref, not ref, but ref, select the matrix that you just put all that information into, which is matrix A. You get all that stuff, which is fun to look at, I suppose, but math, enter, enter, so that you could have the cleaner variation of it. All right, so the interpretation of this is going to be the important piece. Yo. It really just hurt my neck doing that. Sorry. How did I
get to the matrix, like the second matrix?
Second, the inverse key, which is matrix. God. Spontaneous reaction I'm going to pay the price for the next 7 to 10 days.
That, you know what that reminds me? What? The Game Boys? Yeah. The old version, you had the study.
I dropped down a staircase.
Drop myself down the staircase. Twice in 2 days. Like, I don't recommend it. So. The worst is on the second day when you're at the top of the steps and you're thinking, glad I got that out of my system. No way that's going to happen 2 days in a row. Boom. Not good. Not good. So, anyway, the coefficients here correspond to the coefficients in the original equation. So, let's go back to that. And there we are. So now it's a matter of just kind of taking this information and having it correspond to something more meaningful, right? So if we started off with 2x plus 1y plus 1z equals 1, and that simplified itself down to 1x. I'm going to write it below. This is really 1x plus 0y plus 6/13 z equals 9/13. Then we have 0x plus 1y plus 1/13 z is equal to negative 5/13. All right? Which doesn't look like a parametric equation at all. It's definitely not a vector valued function, so now what? Right, so here's the thing. What I want to do is I want to rewrite each of these equations so that they're solved for one variable in terms of some other variable. It looks like it's going to be very easy to solve for x in terms of z, and in the first equation, and solve for y in terms of z in the second equation. So I'm looking at x equals 9/13 minus 6/13 z, and I would also have y equals negative 5/13 plus 1/13 z. All right. Now, minus. All right. So then the question would be, okay, well, what's z equal to? Well, it can't be equal to nothing, right? It's got to be equal to something. Is it equal to something in particular? Maybe. But there's no indication that it's equal to something in particular. So really, since x is dependent on z and so is y, it's not bounded in any way. We don't have any restrictions on z. So therefore, z would be some value z.
So it looks like it's what we would call a free variable, right?
Exactamundo. So that's exactly what it would be. It's a free variable because it could be anything. Its domain is unrestricted. All right. So how do we redefine this? Well, we could leave it like this, I suppose. But if we're thinking about parametrics, we generally define parametrics in terms of t. So t represents time in most cases, but just last class we let our parameter equal s. We've let parameters equal theta before. We could let a parameter equal z, but if we want it to be some completely unknown quantity, what I could do is let z equal our parameter t, in which case we would have x equal 9/13 minus 6/13 t, y would be equal to negative 5/13 minus 1/13 t, and z would be equal to t. Now, does z have to be equal to t specifically? Well, I don't know.
Anything else?
It could be anything. Well, the issue is we don't have any context here. So t, since it represents time in most cases, the flow of time is different in particular situations. I mean, you could even think of time moving at different rates, but you could also think about just simply the units of time. If it's hours versus minutes, it could be apples and oranges depending on how you define things. So at this point, we would just say z equals t, but maybe you want to clean things up. Maybe you want z to equal 13t. If that's the case, then these guys would clean up a little bit. There's no restriction in what you can let your value of t be equal to.
I was about to say, like, is it wrong to think of it because it's two planes intersecting? They're kind of like just functions of z, different x values and different y values for every z. Like, it's a line, and z is going off in different directions. Like,
Right. Yeah. So exactly. So you're going to have differing x and y values depending on what your value of z is. So at different levels, different heights, you're going to have different values of x and y. So whatever you define your z value as is going to be sufficient as long as it supports the idea that it represents a height at some point along the curve. In this case, it's going to be a linear relationship, but it could be a curve. So in vector valued form, we would say 9/13 minus 6/13 t, negative 5/13 minus 1/13 t, comma, t. Right. Now, do we have to write it as a vector value function? No, not necessarily. You've satisfied the requirements of the problem by writing it in this form. This is how we write parametric equations. Just now we're moving towards writing them in vector form, but there was, unless I forgot, which can happen, said find the intersection of the planes. It didn't say to represent your answer in any particular form.
I was going to say, is there something like that in GeoGebra where you can draw the two planes and then draw that line?
Funny you should mention that. So looking at GeoGebra,
It's interesting. I can already imagine how it looks.
so let me get my two original planes in. I'm gonna. Oh, one of them is a holdover, so I can keep that one. The other one was 3x
3x minus 5y plus z is equal to 4.
All right. So that's the intersection of planes, and you can see there is a path there, and that path would be a linear function. So a way to handle that would be to say intersect. Intersect, not intersection, between D and F. There it is, right? So this doesn't look anything like what we just came up with, but that's not a problem because this is a Lagrange. We'll get to that. And it seems like I'm trying to impress people now, but we're going to learn about Lagrange multipliers later in the unit. But this is along those lines, so it's not a parameterized relationship, but it plotted it correctly. That definitely looks like the path that we had in mind. So let's see if our equation is going to stand up to this. Curve. We have
9 over 13
9 over 13
minus 6 over 13 times t.
minus 6 over 13. I'm going to use that multiplication symbol, just play it safe, times t.
Negative 5 over 13 minus t over 13 or 1 over 13. Doesn't matter.
T over 13 sounds good to me.
And then t is the.
And then we can give it some width, so I'll go negative 10 to 10. If it's not good enough, I'll adjust it.
Oh, wow.
All right, so
Wait, why'd you have to do 10 to 10?
just to give it some domain. because if I don't, then it's not going to know where to start and stop it. All right, so, well, the path was there before. Let's get rid of that. You can still see that there's still a path there. Let me get rid of this one. Oh,
It's not the same thing.
it's not. Did I type it in wrong?
Oh, sorry, it's not minus 1 over 13?
Oh, minus 1 over 13. Oh, wait, minus 1 over 13t, though. No, that's
Which is
fine.
the same thing.
Yeah, what did I screw up?
Those are all the same values.
Those are.
Or did we do it wrong?
Pos. Double checking. Double checking. 5, 1, negative 4. You know what's concerning, though, is that I don't see a z equals here, so I'm wondering, that happened here. You see I have a z
Can
equals?
you put another t up there?
I thought I did. It's right there.
You need your z term, maybe
Or should we have left it as
it's.
z?
Do you define? Are you defining and giving it a z term for the same one? So are you supposed to define t for the whole?
Oh, thank you.
Yeah.
Thank you. I need another, yeah.
Why do you need another
Because you're defining t.
Yeah, because t for the z term, and then t to say that this is my variable.
Right.
Ay, ay, ay.
Oh, there it is.
Yeah.
that's the
Oh,
only-
hold on. There it is.
There we go.
Wow.
See?
Okay.
It's there now.
Defining your-
Yeah, I just left it. Okay, so, well,
Right.
it's important that the math was right. So that's good, but that was a red flag. If you, I mean, you're supposed to have 3 variables, so if you don't, then that's an issue. All right, so that's good news. Anyway.
It's really cool.
All right, so the last thing that we're going to cover tonight is the distance between a point and a plane, which I should zoom in on for you. Oh, not reset. That's not what I want. All right, so find the distance between a point and a plane. So we have some point x1, y1, z1 in a plane that contains x sub o, y sub o, z sub o, and that's normal vector n. Compute the projection of the displacement vector from P to Q onto vector n. All right, so this is really just kind of the nuts and bolts of it. You have the plane equation. So here it's written as ax plus by plus cz plus d equals 0, because since d is some arbitrary constant, d could take on a positive or negative value. So whether it's equal to positive d on the right or a positive d on the left, it doesn't make a difference. And you have a normal vector that's a, b, and c. The displacement vector is it's just the subtraction of the different components. All right, so from the component form of qp upon n, right? So qp as a projection in the direction of n, right? So in real, I'll just do a little hand waving here rather than going through the entire proof because time. I'll start off next class with the proof, and we'll go from there. But just give you the general idea here. I'm looking for the distance between point P and the given plane. All right, so I'm just going to highlight that real quick. That's this guy over here. All right, now my normal vector could be pinned at any point on the plane. Right? It may not be anywhere near the point on the plane that's closest to the point in space. If that's the case, you might say that, well, what's the point of having that piece of information? Right? The idea is that if I can take this line, which would be a particular vector, and project it onto vector n, which is that normal vector, all right, so this would be the projection. Upon n of QP, if I can take the component of that, so the projection would be really the amount of this vector that's acting in the direction of that. So if I were to take just just kind of the imaginary piece of this vector, the part of it, just the ethereal part of it that's acting only in the direction of n, and just kind of grab it and push it in the direction of n, that would be the projection upon n. If I could find the value of that, that would be the component that of QP that's acting in the direction of n. Right? So why would that be meaningful? Well, that would give us a length. That length, this length over here, might not seem meaningful until you realize opposite sides of a parallelogram are congruent. So if I know this length here, then I know this length here. And that's the one I need. So if I can find the component of QP acting in the direction of n, then I will have the distance between P and the plane, the shortest distance between P and the plane. So that's the conceptual piece. I'll get into the proof next class. But that leads us to this idea, the component of QP in the direction of n, all right? Which in turn simplifies to this formula, right? And that's where the proof will come into play, because we went over how to derive the component form of a vector last unit, but it's not fresh. So I'm going to take you through it from top to bottom next class. All right? But the good news is it's pretty procedural once you have this relationship. All right? QP dotted with n over the magnitude of n. All right? So n is our normal vector related to the plane. So n in this case would be 1, 1, 1. All right? We have a point P. This is a point in space. The one thing I seem to be missing is a point Q. All right? Now, something I alluded to is the fact that I don't really care what Q is. As long as it's a point on a plane. So Q must be a point on the plane. I don't care where it is, though, which is great news. Wonderful. I mean, it's the best possible news. What that means is if I can come up with an x, y, and z value that satisfies this equation, I'm good. And anything will do. So Q, all right, I'm going to let it be 1, 1, and whatever z has to be in order to equal 4. So 1 plus 1 plus meh equals 4. Meh would be 2. All right. You might say, all right, I want to go even simpler. 0, 0, and then what? 4. Right? Anything that satisfies this equation would necessarily be a point on that plane. All right? If you want something bigger than 4, maybe you were like, okay, well, I'll call your bluff. 10 and 10. So 20 has to be negative 16. All right? Also a point on the plane. Any values that you plug in here for x, y, and z that satisfy this equation will be a point on the plane. So really, you can't go wrong with that. Right? The only way you can go wrong, I suppose, would be if you didn't know to look for a point Q. Because you might look at a problem like this on a test and say, you didn't give us enough information, how am I supposed to do it? Right? When you realize, well, you had enough information all along. Right? So that could be kind of frustrating. So anyway, Q to P. And I'll write P right next to it, just so I can point at stuff. So 3 minus 1, 1 minus 1, 4 minus 2. So I guess I'm not really pointing at anything. 3 minus 1 is 2. 1 minus 1, 0. 4 minus 2 is a 2. 202. All right, so that's my QP. I need to dot that with n. It's really kind of, if you like math, it's kind of cool, this particular topic, because I'm going to show you, you remember optimization from Calc 1, finding maxes and mins. I'm going to show you optimization in 3 dimensions, in 3 space. That'll also help you find the distance between a point and a plane. And it'll give you obviously the exact same answer, but in a completely different way. And like I said, if you like math, you'll look at that and say, oh, this is cool stuff, you know. I think this is the probably the cool math course. I mean, forget about grades and stuff because like that makes everything not cool. But like the material itself is stuff that's cool. It's interesting in a pure math sense. And I get on my soapbox and I forget what I'm doing. All right, so I think I did it right. So 4, hopefully. Now the magnitude of n is what I need. And I mean, that probably couldn't get any easier, unless it was all zeros, I guess. So root of 3. So the distance would be the quotient of the dot product of QP and N. Now, it's an absolute value symbol over that. I mean, absolute value often means magnitude, but sometimes it actually just means absolute value. What it's telling us in this case is if we got a negative number, drop the negative. All right. So in this case, it was positive, so we're good. So 4 over root 3. And radicals on the bottom of fractions, because I know somebody, I forget who it was, it wasn't a bad question during the test, asked if you needed to rationalize stuff like that. You know, even if I required you to, I'd forget to take off anyway, so don't worry about it. Question?
Wait, pressure for Q, where'd you get the 2? There's 1, 1.
This 2?
Yeah.
I assumed 1 and 1, so if I plug a 1 and 1 here, the only value that would satisfy this equation would be a 2.
Oh, okay.
So whatever you decide on for x and y, you have like in statistics we'd call that degrees of freedom. You have 2 degrees of freedom in a 3 variable system. You have freedom to choose 2 of the 3 variables. The last variable is automatically determined based on the structure of the equation. All right. So, like I said, if you wanted x and y to be 0, then z would have to be 4. All right. So the math takes over once you decide on your first 2 variables. All right. Now, number 11, I'm going to put a star on, and that's where we're going to end class, just to give you a little bit of a taste of what you're expected to do there, because it just seems like, yeah, I'm doing all the easy ones here. What's the deal here? I'm actually leaving a pretty manageable one for you. You see here they give you 2 planes. You know what to do if you have a point in a plane, right? When they give you 2 planes, you can still make it a case where it's a point in a plane. Because if you choose a single point on one plane, and you're looking for the shortest distance between that and the other plane, okay, cool, you do that for 1 point, you do the same thing for 10 other points, it's going to be the same distance, because they're parallel to one another, all right? So in your first equation, come up with a point that satisfies this equation, all right? So guess an x and a y and come up with the corresponding value of z. That'll be the point, like in number 10, and then work off of the other plane. All right, so you come up with the point for the first plane, and then you get to work on the problem just like it was question number 10. All right, so that every time it changed the slide, it's hit or miss as to whether or not it starts. So what we did was we took the plane and we established a point that was on the plane. All right, so in number 10, we were given a point that was floating in space. We needed to find the distance between that and the plane. So we chose a point that we knew was on the plane. The way we handled that was by selecting an x and a y value and then determining the z value that corresponded with the x and y values that we selected. So we chose 1 and 1 for x and y. The equation determined that z had to be 2 in order to satisfy that model. All right, if I chose 0 and 0 for x and y, then z would have to be 4. But regardless, we came up with a point that's definitely on the plane. All right, so in order to carry out the process, I need vector QP, which is the vector between your selected point and the point in space. All right, we dot that with the normal vector, and then divide it by the magnitude of the normal vector. All right, so it's very procedural at that point. The tip that I gave you from, or for number 11, had to do with the idea that you weren't given either a point on the first plane or a point in space. But since you're looking for the distance between two planes, you know that the quote-unquote point in space has to be on one of the two planes. All right, so I'll draw a pair of parallel planes, or attempt to draw two parallel planes. Suspend your disbelief. All right, so we'll have a point here. We'll call it point P. And then we'll have a point on the other plane that we'll call Q. No guarantee that they're lined up perfectly. All right. I just need a point on the first plane and a point on the second plane. One of them will be Q and the other will be P. I don't know which plane is which based on those equations. I don't have GeoGebra open. I also don't particularly care. So what I can do is just call this one to, well, let's keep the color coding consistent. Call this one 2x minus 3y plus z equals 6. And call the other one 4x minus 6y plus 2z equals 8. All right, so I need a point on each one. All right, so for the first one, I'm going to select for point P. I like to keep it simple wherever possible. 006, exactly. All right, for the second one, you could go the same route to like 004. Now, the temptation might be to say, oh, well, just subtract them and you'll have it. But there's no guarantee that these are oriented in a horizontal fashion. It could be on a diagonal fashion, if you know, kind of like skew lines, but for planes. If that's the case, then the distance, the vertical distance, for example, between 004 and 006 might be irrelevant because I want the shortest distance between two planes. So that wouldn't be a vertical distance. Right? It would be some skewed distance. All right? If that's the case, I still have to use this approach. Right? However, finding things like vector QP and a dot product are going to be much easier because I selected really convenient values. All right? So QP (0, 0, 2). The normal vector, all right? So that's kind of the only issue that we're going to be dealing with here, all right? The normal vector, in the previous one, it was obvious, 1, 1, 1, because they only gave us one plane equation. Here we have two plane equations. So then it becomes a question of, all right, well, which plane am I looking at? I need the vector, the normal vector associated with the plane whose point I designated as Q. All right, because that's how the function or the model works, or the, however you use that word, the distance formula. All right, Q must be a point on the plane, that specific plane. All right, Q came from the plane 4x minus 6y plus 2z. So that's the plane that we would designate as having the normal vector n. All right, so I'll just go with the colons. 4, -6, and 2. All right, so I need to dot QP against n. And like I said, very easy calculation in this case because we designed it to be so. All right, we selected convenient x and y values, settled with the idea that we'd have to figure out z, but that wasn't even hard. But that makes the dot product that much easier. All right, so the x and y terms or components are going to zero out, and so we'll just be left with, I'm sorry, I pointed to the wrong thing. The x and y would zero out, and then we would just be multiplying the 2 by the 2 and get a 4. All right, so that's nice and neat. I need the magnitude of n. So 16 plus 36 plus 4. All right, so that's what, root 56? And then it's just a matter of putting it all together. I mean, there's really not much to put together. It's distance is the absolute value of the dot product of q, p, and n, which is 4, over the magnitude of the normal vector, which is the root 56. All right. The absolute would only come into play if I had a negative quantity. So if my dot product, because I wouldn't be worried about the magnitude being negative, if the dot product gave us a negative result, then that we would drop that negative, but that didn't happen.
I still wasn't clear of why you chose the second equation to be the normal vector.
Oh, that's because of consistency. Since Q has to be a point on the plane that we're referring to is the plane with the normal vector n. So once I decided that point Q was going to be 0, 0, 4, it came from this plane equation. So that must...
At the very beginning?
Well, it just kind of worked out that way. I didn't consciously make that decision. What happened was I just started drawing a picture. I put a P there and a Q there, and then I said, okay, well, let me put this equation here and that equation there, and then go off of that. Had I gone the other way, had I called this point Q and that one P, then that would make this the plane equation that I would pull the end from.
No, I know, that makes sense. I know that the second equation, no matter what, would have been your normal vector. I just don't understand why it was that specific equation. You said that was determined at the very beginning because of consistency, you said.
Oh, it was
The
kind of.
4x minus 6y plus 2z is equal to 8. You said
The
whether you call it
consistency-
P, Q, whatever, it's going to be that equation.
Because of how I define Q over here. Once I said Q is coming from this equation, then I established that it must be the Q associated with the normal vector n in the formula. So that put the point P as the point out in space, and this as your baseline plane.
But isn't P also associated with the formula?
It's associated loosely. I mean, we only really needed it to get the point that's floating in space. Because in this case, we were given a point in space, point P. Here we weren't. I needed to come up with a point somehow. So I used this equation to come up with that point, but once I did that, I was done with it.
See, that's the thing. So I feel like I would just guess as to which one to use for the normal vector, and then that's going to give you like a right or wrong answer.
Well, that's the thing. You would be all right, because if you said that this is point Q associated with this plane, then that makes this your point P floating in space.
Mm-hmm.
So then you would have your point Q up here with the normal vector here, and your point P would be 0, 0, 4. It's just things would change in the sense that you would have a different magnitude for your end, and you would have a different dot product, but it would still give you the same answer.
Okay.
So it doesn't matter which one you select. It matters about being consistent once you make your selection.
How about if you were to divide the second equation by 2, like divide through?
It's equivalent.
It would be?
Yeah.
Okay.
So a normal vector, we're not actually taking the difference between the two planes, we're just taking the one that we used for our base point and not the one in space.
Correct. And so what a lot of people will do, because I drew the two planes, what a lot of people will do is not even draw the second plane, just get that second point based off of their knowledge of whatever the equation is, in this case 2x minus 3y plus z equals 6, get a point from that, and then just pretend that it's a plane and a point. You know, establish one plane as the plane, and just use the other plane to come up with a point. And once you do that, just pretend it's question number 10 all over again, just to kind of keep it straight in your own minds. Because sometimes if you trim out a little bit of the fat, everything gets a little bit easier to comprehend.
So I used my n as a product between the two planes, and I just got half of what you got. I got 2 divided by the square root of 14. Would that be okay for the same answer?
Well, so you get 2 over root 14.
Yeah.
I'm just trying to think. Let's see. I think that's equivalent.
It is.
Yeah.
'Cause you can factor out a 4.
Yeah.
56.
Because 4 times 14 is 56. Yeah, that's the reduced form of this.
Oh, okay.
So it's perfect.
So even though I changed up what my n was, 'cause my n was 2 minus 3, 1, which is obviously just divided by 2, what your n is.
Right. Well, that's because they're parallel planes. So one is a scalar multiple of the other. So that's expected. But that process will also work if you had 2 non-parallel planes. So, but it would depend specifically on where they are, within it. So it's a little trickier in that regard because it would depend on specific points. If the 2 planes are not parallel to one another, then you would have to be given a particular point. It wouldn't be left up for you to figure out because the distances between the 2 planes vary depending on where you are. So that's the only exception to these kind of properties. But yeah. Okay, so now a formal discussion on vector valued functions. So we've talked about them. We've kind of alluded to the importance, but haven't really gotten into the bits and pieces. All right, because once you start getting into functions, specifically functions on a Cartesian plane, for example, then you start getting into concepts of domain and range. Then you get into things like intercepts and slopes. And when you talk about slopes, derivatives now become fair game. When you talk about the path of a function, you can talk about the area contained between the path and some other object, so all sorts of different possibilities are open to us now. All right, so at first we're going to talk about sketching a curve traced out by a vector valued function. All right, so and limits, of course. But just like we did with parametrics, we're going to start off with the pre-calc part of it. Although this topic would never be in pre-calc, it does have a pre-calc-y kind of feel to it because we're not getting into derivatives and things like that. And in fact, you could actually categorize a lot of the stuff that we've been doing in this unit as kind of pre-calculus in nature, because really when you think about it, we've done cross product, dot product, we've written the equations of lines and planes, but at what point have we taken a derivative or an antiderivative or a limit? We really haven't. So it's all basically foundation stuff for the calculus. All right, and this is nothing different. All right, so a scalar function, input, output. So a scalar function as opposed to a scalar. All right, so we're gonna have to kind of get a sense of the terminology here. Real number, x in some domain. The output is a real number, f of x in some range. All right, so just as you would always expect. Scalar functions could be used to describe a curve by graphing all points, just as you would expect. So you have something like y equals the square root of 1 minus x squared. And you say, oh, okay, well that's a scalar function. Cool. So it's a function. Well, yes and no. All right? It's a function in 2 dimensions, but how does it play out in 3 dimensions? That's what we're really going to learn about. All right? We could write it as a vector valued function, and there is value in doing that. All right? So we're going to parameterize it with some parameter t. And it could involve 2 dimensions, 3 dimensions, and that's just the beginning, because you could be in a set of 4 dimensions, 5 dimensions, and so on. Right? So, but your components, the number of components, will dictate what dimensions you are working in. Right? So if you had a vector that contained 4 components, you're in 4 dimensions. Right? But the good news is, what works in 2 dimensions for this concept will also work in 3 dimensions, will work in 4 dimensions, and so on. All right, so it's just a matter of getting our groundwork and then going from there. So we have our component functions. Component functions, instead of being just like 2, 3, 4, something like that, it's now cosine of t, sine of t, maybe comma something else including a t. If we want to go into 3 dimensions. But the idea is that it's no longer just a constant or a particular scalar quantity, it's a function in and of itself. All right? And so when you have functions that are incorporated into vectors, they take on particular roles, and we'll have to figure out what those mean. All right? So some definitions here. I think I've pretty much kind of covered all this, with hand waving and everything, but these are the formal definitions. The one important thing here, the vector function r of t corresponds to a family of vectors, one for each value of t in the domain. All right? And so that's an important thing to keep in mind, because when you think of points being plotted, as opposed to vectors being plotted that describe the path, it takes on 2 different forms visually. They amount to 2, basically, when you think about it, a path is a path. It doesn't really matter how the path was created if you're just looking at the path. Just kind of like when you go back to parametrics, when I was talking to you about plotting a curve and saying that we have to indicate the direction of the curve as it's being graphed, if you only cared about the path itself, you didn't care if they laid the tar down this way or blacktop or whatever it is. Like, they're paving the road. They paved the road from east to west or west to east. Who cares? There's a road there. All right? You can now drive on it. All right? But if you're the one paving the road, you might care. Right? And so this is kind of analogized. Jeez, I just made up a word, possibly. I know it's really a word. I've only ever seen it written. It's probably jized, right? Analogized? It just feels wrong. Because it's analogous, but it's analogy.
Analogize sound wrong too.
Yeah, nothing about it sounds right.
Okay, let's add it to the dictionary.
Yeah, just throw it in. I'll put it in the can section.
Always invented anyway.
Yeah, Anglo-Saxon business. So, yeah. Anyway, we're going to have to see what this looks like in terms of a graph. And lo and behold, here we are. So we'll start in 2 dimensions with number 1, and then we'll kick on over to 3 dimensions. Unfortunately, there is no vector value function mode on your graphing calculators. So, yeah.
Program it.
Yeah, program it. The issue becomes, well, there is parametric mode. So when you're working in 2 dimensions, you can pull it off, because if you put it in parametric mode, this would be your x component, that would be your y component, you can get some coordinates. But the minute you throw in the 3rd component, now you don't have a calculator approach anymore. Right? So we're going to learn how to do it by hand, unfortunately or fortunately, depending on how you like to do things. All right, so we're going to come up with a set of t values and the corresponding x and y values. All right, reasonable t values. We probably want some negatives, some positives. You want to get 0 in there, so maybe we'll start with -2 and go to +2. And if we don't have a sense of what the figure looks like after that, then we'll throw some more points in. Fortunately, though, when it comes to vector valued functions, what you see is kind of what you get, because it is still based in parametrics. So if both components are linear, You could strongly suspect anyway. I mean, maybe you're not 100% confident, but you can strongly suspect that the resulting path is going to be linear. Right? If one part of it's quadratic or both parts of it are quadratic, then there might be some uncertainty, but you could probably bet it's going to have some quadratic aspects to it. Right? So just some things to keep in mind. Right? So I pop in a -2. I'm going to get what, a -9 for x? I'm not interested in graphing that. A +1. So a vector. Yeah. So -9, 1 would be my first vector, assuming that I would need to plot that. We'll see in a minute. -5, 3. -1, 5.
0719.
Say it again.
07.
07 and 19. Thank you.
What? How's that 0? Is that 1?
It's not? It happens. It should be 3.
The next one should be 7.
It is. Oh, no, yeah, down below that. should be
Oh, so that's a 7?
7.
All right.
Ah,
Savages. See? Where I'm sitting. It's like you're in the line of fire every day. Make a little tiny mistake and everybody attacks. Like a feeding frenzy. Anyway, so I don't know. I'll just plot the -5, 3, the -1, 5, and the 3, 7, and we'll see where it goes. And it should be pretty obvious where it's going once I do that. So -5, 3. So you might be tempted to just plot a point, but it's not a point, it's a vector. So that's really what we're up against. All right, so again, I'm plotting these 3 for convenience. Oh. -1, 5. Gonna be right there. And 3, 7. All right, now at the tip of these vectors, you have points. So really, what you got to do is look at these vectors as kind of like the legs of a chair or a table. These are the things that are holding up the path. All right. So if you were to continue with infinite vectors, then you would have even more of a sense of what you're up against here. But it does appear to be linear. All right. So we're looking at something like this. Something like that. That's a little bit better. All right, so this is our vector valued function. Let me see, R of t. All right, and just an R of t is all we need. Bless.
So we don't have to worry about like keeping track of the arrows with the parametric. Like,
No, not necessarily, because we don't really have an indication of what the important direction is. So at this point, we're just going to go with the path itself. All right, so that's an important distinction to keep in mind, because when you think about this, there's not points floating in space, points along a curve. Each one of these values, each one of these moments along the function itself correspond to a vector. So a natural question would be, well, how would derivatives work under these circumstances? You know, what would the slope even be related to? The curve, the vectors themselves? What are we up against here? So it's a question that we're going to be working towards understanding as we go forward. But for now, again, we're still living in the world of what do these things look like? Because you might look at something like this and say, okay, I have a fighting chance of understanding what it would look like if it were just the x and y components, because we actually did stuff with this back in the first unit. But what about that t component? Well, let's take a look. Let's investigate.
What's the Cartesian equation?
Sorry?
What's the Cartesian equation?
Oh, I did not do that. Oh, that's funny. Oh, look at that. I didn't even read my own instructions. Yeah, so you have x equals 4t minus 1, y equals 2t plus 5. All right, so t would be equal to x plus 1 over 4. So y equals 2 times x plus 1 over 4. Just a little substitution. So x plus 1 over 2. So 1/2 x plus really 5.5, so it's 11/2. I'm just double checking. Yeah, it looks right. All right, so this would be the Cartesian equation. Now, not too crazy because it's completely linear. All right, it's a linear equation. And you know, you could even eyeball it because, I mean, I know I'm not the best artist in the world, but I wouldn't even categorize myself as an artist. But the y-intercept anyway, 1, 2, 3, 4, 5, yeah, that could be a half. Slope, could it be up 1 over 2? Yeah. Up 1 over 2, up 1 over 2, it looks about right. All right, so just visually we can verify it. But you throw in that extra component, that z component, now what are we looking at? You know, we'd have x equals cosine t, y equals 2 times the sine of t, and then z equals t. Then there'd be substitutions everywhere. How are we going to consolidate that down to a single equation? The answer is not easily, which is also why this question doesn't ask you to come up with the actual equation. All right? We just want the picture. All right, so table of values, a convenient table. Convenience is in the eye of the beholder, but I would imagine the word unit circle would probably be coming to mind for some of us. All right, so some t values that are convenient for the unit circle. Just bearing in mind that the way I labeled this graph, at least in terms of the x and the y value, well, x, y, and z, I didn't label it for negatives. And in fact, we don't really need the negatives, or at least we don't need to force the negatives to happen. They'll naturally occur. So what we can do is just focus on positive values of t, get a sense of the shape, and then if we need to backfill based off of any observations, we can do that. All right, so in terms of the unit circle, what's convenient for one function might not be convenient for the other, but there are some that are convenient for both. Like 0 is generally considered to be nice, whether it's a sine, cosine, tangent, any kind of trig function. All right, anything along an axis is typically considered to be convenient. So you have your pi over 6 and things like that, but let's just jump to a pi over 2, then a pi, 3 pi over 2, and 2 pi, and see where that takes us. Maybe it'll take us someplace great. All right, if it does, then it could be less work. All right, cosine of 0 is what? 1. Sine of 0? 0. 1, 0, 0. So you might be tempted to plot that because that's an easy one to plot. But I would hold off on that for a couple of seconds just to see how the other ones shake out. Because if you create a bad scale to start, you may pay the price the rest of the way. All right. So next up would be, we're going to have 0, 2, and then pi over 2. Times the 2, yeah. So I'm going to write it as 0, 2, and about 1.6, right? All right, because, you know, plotting pi over 2 sounds like fun, but when we're plotting it on a graph, we may want to have the option to go the other way. Because it's about 1.57-ish, so I'm just going to go to the nearest tenth. All right. At pi, cosine is now what?
-1.
-1. So -1, 0, and pi. So -1, 0, and about 3.1. 3 pi over 2, what's cosine going to be? 0. -2. And then we just need 3 pi over 2. Probably should know that. About 4.7. So 3 pi over 2. And really, the decimals are just to avoid having to label our z-scale in terms of pi. I mean, it's not the end of the world if you do that, but consistency in your scales is usually considered to be a good thing. All right, cosine of 2 pi? 1. Sine of 2 pi? 0, and then back to 2 pi. So, yeah. 6.3, yeah, we would go with. All right. So now we got to graph these points. Usually coming up with the points is the hard part, and it's just a matter of plotting them and drawing a nice crappy curve through it. Call it a day. I mean, we're still going to draw a crappy curve through it, but it'll be a little bit more involved. Right? So in terms of the scale, for x and y, nothing terrible. Only going out as far as -2 and +2. For the z, we're going up to 6, so we don't want to go too crazy on that scale. But that's okay. I could just go 1, 2, 3, 4, 5, 6, and then that extra little bit of fluff there will be the 6.3. All right, so that should be fine. And it's going to be floating in space anyway, so it's going to be a little off of that. But those are just going to be my benchmarks. All right, so I'll call this 1. Bless you. I'm going to need to be able to go in the negative direction a little bit. So I'll do that, get it set up. All right, so 1, 0, 0 is 1 in the direction of x, but no change in the direction of y or z. So that's the nice one. All right. 0, 2, and then 1.6. All right. So 0 in the direction of x, 2 in the direction of y, and then 1.6 up. So what I would do is just estimate what 1.6 looks like, hold that distance, and then just shift it on down to 0, 2, and plot a point. All right. So I just got to do the same thing on my little tiny screen. About right there. All right.
Vectors though, right? So
Exactly. So we're drawing little tiny arrows to each one of them. Well, they're little tiny arrows right now. They'll become not so tiny arrows later on. All right. -1, 0, and then 3.1. And again, the benefit of staying with the quadrantal angles, the good ones, the nice ones for cosine and sine, is that we're pretty much living on an axis in some capacity and then just shifting upward from there. All right. So the next one, -1, 0. So -1 in the direction of x, no change in the direction of y, but then up 3.1 units. So I ballpark what 3.1 looks like and just shift it over. So it's going to be about like right there. So it'll look like it's adjacent to the 4, but it's really not. You just have to believe me. Welcome to Calc 3, where you have to believe that the diagram is what it claims to be. These little dotted lines that I draw, you don't have to do it. You don't have to include them. I just do it for a little bit of perspective for my own benefit. It's a way of reminding me personally that this is a point that's in space, right? It's got some elevation. So it's like my own personal code for that point is not on the XY plane, right? If you don't like it, then don't do it. as long as you have the points generally in the right location in space with the vectors indicated, that's perfectly fine. All right, 0, -2, so that's 2 in the direction of y, no change in x, and then upward 4.7. So upward this distance-ish. So like here. It's a thing of beauty.
Oh, that's not mine.
Oh.
Mine looks terrible.
Yeah. After the fourth point, it just became like a blob.
Yeah, it all starts to fall apart pretty quickly, but it also, like, once you have kind of a trained eye for it, it also gets to a point where you kind of start seeing the structure, and for me, everything starts looking like a roller coaster.
I know, I'm gonna say spirals.
It is going to be that. It's an elliptical helix is what it will be. Fun fact.
That sounds like a fun shape.
Yeah. So 1, 0, and 6.3. All right. So 1 in the direction of x, no change in y, and then 6.3 up. So that's the whole length of the vertical axis, really. So something like right here. So basically the tip of the arrow, but maybe a little bit below that. Yeah.
Yeah.
Look at that.
It's really weird point.
Yeah, it's kind of floating in the netherworld there. All right, so we do it in the order that we plotted them. Oh, I missed that. Yeah, but it wasn't looking good, so I'm gonna hide my imperfections with a thicker curve. All right, so that's what it's looking like there, but then it's a question of, like, how does it get to that other one, which is next in the curve?
Towards you, but it doesn't look too pretty.
No, you're getting it the other way. You went in the negative direction.
What?
You gotta come back down.
Yeah,
There
you
we go. And it kind of like curves towards us, I guess.
No, but it still curves upwards. What he drew the first time was right.
Draw something into us.
This is art class, guys.
There you go. There we go.
Beautiful.
Ugh. All right, so
Scrap it from the top down.
yeah, it might have actually been better that way. Let me just do that.
Will be perfect here.
Oh, it looks exactly the same. All right, so here's what it ought to look like. I screwed that up already. Yeah.
Coil.
Yeah, exactly. And then, going on as much as you want. All right.
If you look at it from the top version, it'll just be a circle.
An ellipse.
Ellipse, yeah.
Right, but it would be the two-dimensional rendering of it, yeah. So, but obviously you throw in some more points and get a nice big graph to work with, and actually, while we're at it, make a three-dimensional model. Everything will come out beautifully, but alas, not when I draw stuff. So we bring GeoGebra into the party, because even my "this is what it's supposed to look like" picture, it's still, it's never going to be as good looking as GeoGebra. GeoGebra is the belle of the ball. I do have to log in now. Yeah, here. So, look at this baby. 3 times tangent plus, I, plus 4 times secant j plus 5k. We want to evaluate for these particular points and determine if there's any domain restrictions. Well, the reality is these particular questions are probably going to give us some sense of what the, if any, the domain restrictions are. So R, oh, that's still too thick. I had that on from earlier. All right, R of 0. All right, so what's the tangent of 0? I think I heard somebody whisper it to themselves. 0. I'll write 0i. The fear associated with trigonometry is palpable. You notice that. It's like, I don't want to say it because then I'll be the one who doesn't know trig when all he's been talking about is getting to know trig. Yeah, don't be shy. Don't be shy. Nobody's going to judge you. I mean, I'm sure somebody will, but like everybody's judging everybody at any given moment, so what does it really matter in the end? Secant of 0? 1. So 1 times 4 is going to give us a 4. All right. And that's because cosine of 0 is 1, and secant is just a reciprocal of that. The last part is just a 0. So this cleans up to just 4j. And really, all we're doing at this point is asking ourselves, is there anything wrong with that? Well, what could be wrong with it? Anything that would be wrong in all of your previous math classes with a function is still what would be wrong with these functions, like imaginary, undefined, things along those lines. All right, so R of pi over 2. Tangent of pi over 2. Undefined. So the whole shebang is undefined. All right. With tangent, secant, other kind of trig functions, we're not really worried about it being imaginary. The only way it would be imaginary is if I plugged in something that was imaginary. So I'm not concerned with that, but I am concerned with when it's going to be undefined. All right. So 2 pi over 3. 3 times the tangent of 2 pi over 3 plus 4 times the secant of 2 pi over 3 plus the last one is just simple multiplication, so 10 pi over 3. I'll just throw that in there. All right, so tangent of 2 pi over 3.
That's square root of 3 over 3.
Square root of 3 over 3, but it would be negative. All right. Square root of 3. It's the 30-degree reference angles where it's the other one. Secant of 2 pi over 3. So that would be the reciprocal of cosine 2 pi over 3. That one should be a little easier. Yeah. Reciprocal of a half. 2. So negative 2 because it's the second quadrant. All right. Ultimately, we're just looking to see if there's anything wrong with this. And we didn't get anything undefined, so we're fine. But I'm still going to clean it up, you know, best I can anyway. Okay, so the question again is, are there any domain restrictions? Well, we found one of them. So R of t is undefined when t is equal to pi over 2, but then it's a question of just pi over 2?
N times pi over 2.
And what?
N times pi over 2.
N times pi over 2.
N's equal numbers.
Well, that could work in some circumstances, but then it would be a question of if it's, for example, 2. If it's
Odd numbers.
specifically odd numbers, that could work. So if you multiply by 1, we're good. Multiply by 3, we're good. 5, we're good. Negative 1. Yeah, so we could say so there was another way I was thinking of, but I'll write it the way you're saying. So 2n minus 1, that makes it odd, multiplied by pi over 2.
Series now, I like it.
Yeah, mix it all together, right? So where n belongs to the set of integers will be fine now because I've established that it's, sorry, I just made a regular z for some reason. I've just established that it's going to be odd just based off of that. So that should get it done. Right? But what I was thinking of, you know, not that it's any better or worse, is if you're at pi over 2 and you want to get to 3 pi over 2, what do you have to add? Just a pi, right? Or 180 degrees. So that'll get me to another location which is undefined. If you add another pi, you'll get back to the same location, so still undefined. If you were to go the other way, you'd subtract pi. So increments of pi will get the job done also. So if you were to say plus n pi, where n belongs to the set of integers, that'll get the job done as well. Right, so any expression that allows for you to account for any possible instance in which it would be undefined would be acceptable, obviously. That works. I mean, because I understood things like R for real numbers.
R for radius.
R
They
for
already used N.
they had already used N.
They
Yeah.
already used I.
So they were grasping, basically. I should invent something so they can name it after me, and then that'll throw everybody off. So, limit of a vector value function. So it's like, oh, in what way is this the same or different from limits in x, y planes? You know, ordinary limits. No, not very different. So that's good news. All right. So your limit properties all come into play here, which is actually really good, because you kind of built your understanding of calculus on the concept of a limit, and it would be nice if, as you further develop your content knowledge in calculus, that you can still rely on some fundamental properties. Okay, so we have the continuity rules. Okay, so R of A has to exist. The limit as t approaches a of a function has to exist. Right, so these are all truths, where if you think about it in the function sense, that's saying that, yeah, there has to be a point that exists, but it also has to be along a path. You have to be able to approach that point on your function from the left and from the right if you're working in 2 dimensions. In 3 dimensions, it gets a little dicier. And those two values have to be the same. So if you're dealing with, for example, a piecewise function in 2 space, so something in 2 space, you might have a curve that terminates at a point. Maybe you have an open circle here. All right, and this is all happening at the point where t is equal to a. I can go solid line here. So that's point A. All right, so here we would have the case where R of A exists. So that first condition would be checked. We'd be good to go there. But the limit as t approaches A of R of t, well, first of all, it doesn't exist, so how could it be equal to anything? But it's not equal to R of A. So therefore, it's not continuous. The function would not be continuous, or the path would not be continuous. All right? And yeah, all calculus. Visually, it kind of makes sense, though, because if I asked you, just by looking at the picture, are you dealing with something that's continuous? You'd say no. How do you know? It's not continuous, right? You'd be like, They're two disconnected pieces, so how could it be continuous? All right. Now, if you're dealing with something, for example, also piecewise, maybe there's an open circle there. All right. This would be a case where the limit as t approaches a of r of t, it exists. It would be whatever this value is here. All right, this would be the limit as t approaches a of r of t, with this being the a. All right, so there's a location that it exists, or at least it's approaching a location. The issue is r of a does not exist. All right, so therefore this would not be continuous. But, you know, common sense tells you, yeah, it's not continuous as well. How do you know? Because it's not continuous. All right. One final possibility here would be another piecewise function r of a exists. It's a solid point. The limit as t approaches a of r of t also exists and specifically is equal to r of a. All right. All right, so three distinct situations, but each giving different outcomes. All right. So in this last instance, oh, I didn't write it. Therefore, this one would be continuous. All right. And in all honesty, I mean, I kind of feel like I kind of beat this to death a little bit in Calc 1 without really giving you the payoff, because, you know, what happens? You learn all these rules, and then you pick up a calculator and look at the picture. Like, is the sine function continuous for all values of x? Well, you could do it this way, or you could type in y equals the sine of x and hit graph and take a quick look. Or you could look in the table and see if there's any undefined or imaginary components. Right? Same idea for a rational function. You know, you type in 1 over x and you see that there's an error at x equals 0. Okay, it's not continuous. You look at the picture, you see a big old vertical asymptote there, and you say it's not continuous. Right? So what is really the benefit of this? I think I kind of alluded to it. I maybe even did more than that. There is no vector value function in your graphing calculator. So really what you're doing is you're taking all your knowledge, your accumulated knowledge from two-space, all those things that you were learning to do by hand for no apparent reason, you put it to use here because all of those conclusions, all those observations, they allow you to evaluate situations now when you cannot look at the picture quickly and easily on a calculator. Right? So by knowing this information, these relationships, all this is Calc 1 stuff. You know, I used the Calc 3 notation, but I didn't do Calc 3 work here. Right? It's still in 2 dimensions. All right? But it very easily translates into 3 dimensions. Right? So just by knowing these relationships, everything kind of becomes a lot simpler. All right? So things like evaluating functions and finding limits, they have more meaning for us here by hand than they would in a Calc 1 class. So calculate the limit. Well, what does that mean? Well, algebraically, it would amount to the idea that if you could substitute it in and get a clean result, then do so. All right, so that's what I'll do. So we're looking for the limit as t approaches 3 of r of t. That's going to be equal to, well, I'm going to pop in a 3 for each value of t in this guy here and this one over here. So we're looking at 9 minus 9, so 4. So 4i plus 9j. All right, so it's direct substitution. And there's really nothing more to it than that. All right? The interpretation is more important because what we have are infinitely many vectors for a vector value function, infinitely many, from negative infinity to infinity, as t is approaching 3. Now again, from the left or from the right, well, not necessarily, because we're working in a different realm now. But you could kind of visualize it that way if you need to, where before 3 and after 3, right? So we're increasing towards 3 and we're decreasing towards 3 from positive values, right? Those vectors are pointing in different directions. Eventually, they're either, well, when you get to a t-value of 3, from one side, you're going to be pointing finally in a particular direction, and then from the other side, you're going to be pointing in a particular direction. It's a question of, will they be pointing in the same direction, or will they be pointing in different directions? If they're pointing in different directions, then you have a contradiction, in which case the limit would not exist. If they're pointing off in the same direction, then you know you have consistency, and that would be your limit, right? So your limit is actually a new vector that represents the direction that the path would be going in at that particular moment in time, all right? So, I thought that was a question. The second one is exactly.
Would it be 12j?
Yeah, what would it be? 15?
I mean,
no.
15?
Oh, 15. Thank you. All right, so number 2 is the same idea. Number 3, also similar concept. The last part's a little iffy, so definitely take some time and look at that. But number 4, you see it is a continuous, so it's really a culminating event. So definitely take some time and look at these problems. Just put some stars.
What if you have a imaginary number? Is that still a valid limit if there's an imaginary component?
There would not be imaginary components for any of this. There
Second
can
one
be.
has an imaginary.
So then you toss it. The limit does not exist. Yeah. There actually is an area of study that involves imaginary numbers and this material, but that's different. It's a specialized course. I think they still teach it in the 4-year. Functions of a complex variable. Just basically functions that are defined in terms of complex numbers. So interesting stuff, but unrelated, or at least not directly related. So the calculus of vector valued functions. Look at this beauty. That looks familiar, right?
Mm-hmm.
Yeah. That's good news and bad news, depending on my mood for today, I suppose. It would be good news in the sense that, oh, that means calculus works the same way for vector valued functions, because that's a difference quotient. Difference quotient, you know, f of x plus h minus f of x all over h. Or use delta x's if you have that teacher that was an overachiever. But here you have delta t, because it doesn't really make sense to say h in this context. H in the f of x plus h made sense because it was a horizontal change. This is usually representing time. So if that's the case, does time move horizontally? Well, it depends on how you graph it, but time itself doesn't, you know, so it doesn't make sense to call it there. So I had to relent and actually use a delta t, and it just sapped my life force to do it. But that's okay. The derivatives, but if you look at the derivative of a vector value function, look at the original function and look at the derivative, and it really could not be any easier. Now, there is drawbacks to everything, because I tell you that all you have to do is take the derivative of each part, but then you see a natural log in there, and you think back to the last unit test and think to yourself, oh yeah, I did tell myself I was going to study those rules. But yet here I am again, having not studied those rules. So that could be an issue. If you don't know the facts related to it, that could be a problem. If you do, then there's nothing to it. All right. Yeah. There's going to be more with logs. So if you've been putting that on your list of things to do, put it on the done list or something. I don't know. Just get it done. Get it done. That's right. So anyway, I said that it's good news or bad news depending on my mood on that particular evening. This is the particular evening. And my mood drives me in a direction that does not require you to use the difference quotient to find the derivative. Right? So you remember that back in the day? If you don't, then maybe that teacher didn't bother with it either. The one where you had to actually compute f of x plus h minus f of x, simplify it all, and then apply the limit. You did that for like a month and a half before you learned all the shortcut rules in like one class.
Yeah.
And then it was like, wait, could have done this all along?
Mm-hmm.
What's that all about? You know? And then if you had a friend, or maybe you had some prior knowledge, there's always some like cool person. Like if you're like an elementary school kid, you want to hang out with the big kids. They're like, yo, you ever watch this TV show? It's got like bad words in it, but it's so cool. And if you watch it, you'll be cool too. Like the equivalent to that on this level is the person that says, yo, I got something for you, man. It's called the power rule. It's like the coolest thing, man. Stick with me, kid. I'll show you some things. It'll open your eyes, you know. And so you did that, and you thought to yourself, forget this difference quotient business. I'll just use the power rule. Until there were like 3 questions on the test that said, find the derivative using the difference quotient. And you're like, oh crap, what do I do now? Because I didn't learn that or bother to try. And so you bombed the test. And yeah, it was heartbreaking.
Is that a personal story?
A personal story involving me with a red pen. So
Oh, okay. That's you. That's you.
the other way around, yeah.
You knew who it was.
Yeah. I mean, I just listened to my teacher when they told me something was important. I just assumed they weren't saying it for the sake of saying it.
So funny.
They're like, study this because it's going to be on the test. Okay, will do. And then lo and behold, it was on the test. And then I got it right. It was great. You know, but there are plenty of people who didn't. They're like, you never said this is going to be on the test. And then I was the one that they pointed to and said, well, then how did he get it right?
You know what's worse though? When your teacher tells you this game on the test, that's not on the test. You wish
Or
you
no,
had
they don't
studied.
tell you anything, but it's something that just randomly appears in the test that you don't even know.
Oh yeah.
Oh,
Better.
that's probably the worst.
Yeah.
Because if you're over prepared for something, that's one thing.
Mhm.
But if you're completely blindsided by something, that's completely
I
terrible.
had this teacher Cooper. There was just a practice quiz, and he says like, yeah, everything on the practice quiz will be on the test. What we'll go with a different teacher with the practice quiz and be like, half this is wrong compared to what the answers he gave us.
Ugh.
Yeah.
So the only thing that was consistent was the question numbers, basically.
Yeah.
Yeah, there will be a question number 1 and a question number 2, and that's about it. Brutal. I mean, the only time that I ever do that, I don't do it on purpose. It's like I get in a groove during a lecture, and I say, yeah, this is totally going to be on the test, and then I just flat out forget to put it on. Like that's the only time that ever happens. But most people are all right with that. So the derivative is just the derivative of each part. So sine of t squared, chain rule, is going to be sine becomes cosine, so cosine t squared times 2t. So 2t cosine t squared. Bless you. So that's that guy. This guy is a product here, so that's fun. So we'll do a little first times the derivative of the second. So t minus 1 multiplied by the derivative of the natural log of t minus 1, which would be what? 1 over t minus 1, plus the second times the derivative of the first, which is just ln of t minus 1. All right. Then the derivative of the tangent of e to the t. So that's going to be
Wouldn't, I was thinking about like if that was chain with a u, but that just was a 1.
change with the what?
Nothing, I was thinking of like in chains.
Oh, okay. Yeah, if the inner function is more elaborate, yeah. So tangent is secant squared,
E to the t
e to the t
times e to the t.
times e to the t. Now, depending on the instructions, this might be sufficient. Oh, sorry. This may be sufficient. If it says simplify, you got to simplify. All right, but it also asks us to address the domain, so we'll do that as well. So 2t cosine t squared, comma, 1 plus the natural log of t minus 1, comma, e to the t secant squared e to the t. All right, so we have to evaluate this for the domain. There would not be an expectation that you'd have to graph anything like this, because that would just be horrible. But something like evaluate it, that's fair game. Make a determination of the domain, that's also fair game. So you look at each component and just observe the relationships.
Aren't they still restricted by their original domain?
Restricted by the original domain and also any considerations that emerge through the differentiation process. Because sometimes you could have something that exists in the original function, like for example, you have something like the square root of x minus 1. You take the derivative of that. When you do that, you took something that was defined for, well, what would it be, x, for all values x greater than or equal to 1. But then it removes the 1 from a possible value because now it's in the denominator, right? So there's that idea. But we can do a little compare and contrast between the first function and the second function, and the derivative function, and we'll note that there really isn't anything to worry about in terms of new information. And that's because this is everywhere continuous, because it's a product of two everywhere continuous functions. Right? We have a linear multiplied by a trig function, that's fine. And that trig function is composed with a polynomial function, which is always continuous. Right? If there was a radical in there or something, it would be a different story. As compared to the sine of t squared, which is a simpler version of this, so always continuous. Ignoring the middle one for a second, we can look at the tangent. Tangent functions, they exist wherever cosine is not equal to 0. Right? Because tangent is equal to 1 over cosine. Compare that with the secant squared, which is 1 over cosine squared. It's essentially made up of the same ingredients. Right? So what I need to do is figure out really two things. Anything that's going to make the natural log exist. Right? So I need t minus 1 to be greater than 0. And I also need cosine of e to the t to not be equal to 0. Those are the two things I have to worry about. Right? And again, just to kind of make sure that that's crystal clear, that comes from the idea that tangent is sine over cosine. And it's the cosine being equal to 0 that would make it undefined. Right? Now, sometimes just a matter of like looking at it to realize what the concerns might be. So, just kind of play this out in your mind. E to the t, right? It's always going to be a positive number, that's true, because no matter what you put in for t, it's always going to be equal to something positive, because positive rates to a positive. So we don't have to worry about negative angles. The only thing we would have to worry about is any instance in which e to the t is equal to pi over 2 or some multiple of that, right? Some pi rotation of that, right? So what I'm looking for, because again, cosine of theta is equal to 0 if theta is equal to pi over 2, 3 pi over 2, etc. I just need to know when e to the t would be equal to pi over 2, 3 pi over 2, etc. All right? Because the other part's easy. I just add a 1 to that and I'm done, right? Just take care of that right now. T has to be greater than 1. It's really the other part that I'm worried about.
Wait, so are we making sure that RT doesn't have those numbers, or R1T?
Either one, because tangent is sine over cosine, and also secant squared is the same as 1 over cosine squared. So what exists for one will exist for the other. But it's always a good idea to look at your original function when talking about the domain first, because if, and this goes back to Calc 1, if it's not continuous for the original function, it's not going to be differentiable. All right? So if we can establish lack of continuity in the original function, then we don't even have to worry about it in its derivative.
Okay.
So now, also just keep in mind, and this doesn't happen here, or not necessarily, we'll look at it in a second, but let's say, for example, this said t is less than 1. Or maybe, yeah, I'll just go with that. I'm just trying to think of a way to make it crystal clear. Regardless, it is possible that one part of your domain could allow you to ignore the other part. So if this said something like t is less than 1, and you see that this is equivalent to 1.5 and so on, you know, you might be able to disregard all these values, but that's not the case here because you could also go in the negative direction, so it's kind of not the best argument. Anyway, I got to figure out what t would be. So let's take a look at just one possibility for a sec.
Just natural log at all.
Yeah. And that's really the conclusion I'm going for. Because if I convert e to the t equals pi over 2, that would give me t equals the natural log of pi over 2. So that wouldn't be any different for 3 pi over 2, 5 pi over 2, negative pi over 2, negative 3 pi over 2, all of those possibilities. All right. So I know I have to be greater than 1. I do want to look at the decimal value of the natural log of pi over 2, because it might not be relevant. Right, so 0.45, so that one would be irrelevant. So the next candidate would be the natural log of 3 pi over 2, because I'd be looking at this guy. So ln of 3 pi over 2. 1.5, so that's just short. All right, so don't need that, don't need that. The next one would work.
Wait, wouldn't that work though? So 1.5.
1.555.
Well, 1.550, yeah.
Oh, yeah, you're right.
Greater than 1, so it works.
Yeah. For some reason, I had it in my mind that it had to be greater than pi. Pi over 2, sorry, which would have been 1.57. All right, so that's a good one, and then anything beyond that would be fine. All right, so at long last, I think we have it where specifically, right, so it's just kind of a weird thing to write, the domain would be t such that t is greater than 1 and t cannot be equal to, now we just have to state every pi rotation from 3 pi over 2 in the positive direction, because the negative direction doesn't make sense, right? So we're talking ln of,
Why not just say theta?
We could incorporate a theta. So plus pi theta. Where theta belongs to the set of, well, it wouldn't be integers, it would be the set of natural numbers.
Sorry, why did you get rid of pi over 2 again?
Because it was,
Redundant.
Because it's already stated. Right?
it was too small. No, the natural log of pi over 2 is 0.452.
And it was stated when you said that t has to be greater than 1 in a previous part, right?
So that's why it's being redundant. It's already less than 1, so the original
Right.
restriction was
Yeah.
t is greater than 1. So it's like, okay, you're repeating yourself.
Exactly, exactly.
You wouldn't get points off, right? If you made that if you stated that?
Well, if you included a pi over 2, natural log of pi over 2, that would be fine because you're saying it can't be included. And since you've already said it, yeah, it's redundant, but it's not wrong.
Okay.
Yeah. It's just a little overkill, but we can live with it. So, derivative part, you know, the calculus stuff, not bad. Little product rule, little chain rule, nothing too crazy. All the pre-calc stuff that followed that was what made it hard. And it's all pre-calc. Can't even blame it on Calc 2. Like, oh, Calc 3 is hard because I don't remember anything from Calc 2. No, it's not even Calc 2. Actually, think about it. What Calc 2 have we done in here?
Did earlier with the series.
The integration with the
Yeah, for
the graph between two graphs.
yeah, so we did it for like a second.
Yeah.
And then we did that on our calculators too. And it was like,
You didn't have to do it really.
yeah. So it's like,
Just gotta remember it exists.
yeah, exactly.
Thing.
Yeah, Calc 2 is like a mythical thing that existed at one point. But really, it's all the pre-calc that makes this stuff tricky, right? Because honestly, you gotta be able to conceptualize this in a way that makes sense, and that way involves you being able to look at the tangent and the secant and realize that they're essentially going to have the same domain. You know, without a strong background in pre-calc, it does take a little bit longer for that to sink in, but it's still there. You know, it's still well within the realm of possibility, but it takes a little bit more work. All right. All of this stuff down here, some of it seems pretty obvious, like the first two. The sum of two vectors, you know, vector valued functions. And the derivatives are the two derivatives added together separately. You have a constant multiple. Same as a constant multiple in Calc 1. But then you could have a scalar function, right? So a function like, for example, y equals x squared. In this context, when we're looking at vector value functions, an ordinary function written in that notation is known as a scalar function. It is treated kind of like a constant multiple would be treated, but it also has a product rule associated with it, right? So think of it this way. If you have a scalar function multiplied by a vector value function, the derivative is gonna follow the product rule the way you would expect it to. All right. So first times the derivative of the second plus the second times the derivative of the first, or
What?
however you like to do it, like product rule.
Yeah, right backwards though.
Now, yeah, for some reason textbooks do it that way. I don't know. Like it just sounds weird to say it that way. But when you're dealing with dot products and cross products, you know, it has the same structure. You know, you can follow. I mean, they're just letters on a page. They look the same as, you know, for example, the scalar function, but you know what you're going to do with them are extraordinarily different, right? Because you're finding the dot product between two vector valued functions, one of which is a derivative, but multiplying a scalar function by a vector valued function is way different from a dot product or a cross product. So if you look at the structure of it, it looks very much the same, but it has massively different different approaches. Implication of a zero derivative, very rare that I include like just full-blown text like this. I mean, aside from like an introductory thing, this is very important. Recall that for a scalar function, that any extrema of f would only occur at a critical value, which is defined as any x equals a, such that f prime of a equals 0 or is undefined. Right? That's the first derivative test from Calc 1. So you take the derivative. What you do? If you're ever in doubt in Calc 1, you take the derivative, set it equal to 0, and solve. Right? The one drawback to that is that sometimes you can get a critical value for where it's undefined, like if there was a cusp. So it's a little bit of a tricky situation. For a vector value function, it's not the same. All right? So if your vector value function has a derivative equal to 0, it can result in cusps in the curve traced out by the function. All right? So just as a refresher, a cusp looks something like this. So it kind of bows into a V shape. All right? That's not the only way a cusp can look, but that's the classic image associated with it. All right? The emphasis is on the word can. Therefore, we say that a curve traced out by r of t is smooth on an open interval if r is continuous in I, and the derivative is not equal to 0 except possibly at the endpoints. Right? So we may not be looking at something that's smooth if the derivative is equal to 0. Right? So this is kind of like the opposite, not the direct opposite, but it has kind of opposite parts to it from the first derivative in function-based calculus. You take the derivative, set it equal to 0, that's how you got your turning points. All right? Those are the things you were looking for. Here it's more like those are the things you're looking to avoid. All right? So it's a very, very different way of thinking about things. So in Calc 1, your default was take the derivative, set it equal to 0, and solve. Here, you very rarely want to do that. Oh, that is not my my scroll tool. So we have two vector valued functions, and we have to find the derivatives. And you could do it with, first times the derivative of the second, or you could follow the model. Derivative of the first times the second feels weird to say it that way. The way that you're going to want to handle this is to find the derivatives of each vector value function before you even get started on the process. All right. So just off on the side, I'm going to figure out r prime of t. And at least to get us started, I tried to include things that were relatively simple. No trig or anything like that. Some linear functions and stuff like that. So we're looking at 6i plus parentheses 8t plus 2j and then plus 5k. And then we have 2t I plus 2j plus 3t squared minus 3k. And at any point, if you want to kick over to vector notation, you're fine. IJK notation is fine too. They're interchangeable. It doesn't matter. All right. So I'm going to take my derivative here. The derivative of the product of vectors, vector value functions r and u. So r prime of t dotted with u of t plus first time r of t. See, I'm doing it by the formula and I don't like doing it. U prime of t. All right, so we have to dot the appropriate components together. could be a lot of writing unless you could do some of this on the fly. So I'll try to color code it a little bit. So I'm doing r prime against the u. So it's going to be 6 multiplied by the components of u, or at least to start. So it's going to be 6t squared minus 18.
So that's the entire thing is I, right?
That entire thing is going to be I, yeah. Then I'm going to tackle the j's. So I'll have to use distributive property.
Why did you add I at the end?
Oh, I have no idea. Habit.
Because I made the comment.
We'll go with that, yeah. I needed a good excuse, and you just gave me one. All right, so I'm going to distribute the 8t plus 2 against the 2t plus 4. So that's going to be 16t squared. And our outer is going to be, what, 32t plus 4t, so 36t plus 8. At least we end easy here, or at least for this part. So 5t cubed minus 15t. All right, so that's the first part. Now, if you're thinking in your mind right now, dang, the next one's a cross product. Yeah, it is. It sure is. All right, so then I'm going to tackle the second part, which is r dotted with u prime. So it's going to be these guys multiplied, or dotted. So 12t squared plus 16t. All right, then I want to do red for the second part. That part's not too bad. I mean, it's not bad at all. So 8t squared plus 4t minus 6. And the next part isn't bad either. We're just taking 5t and multiplying it by 3t squared minus 3. All right, so 15t cubed minus 15t. Oof, combine like terms, yeah. Try to see most of it on my screen here if I can.
20t cubed.
So we got this one. Yeah, you got 20t cubed. But then you have to do the proof. What do we got? 6t squared, 16, so 22t squared, 34t squared, 42t squared. Then 36, 21, 37, 41, 26?
Take your word.
Yeah, at this point, it really doesn't matter what it is, right? You just want to get out of here. I could be putting up, like, smiley faces, and that would be fine.
That works.
So, negative 10,
-16.
negative 16. All right, and so that would be the derivative of the dot product of the vector value functions u and r and u. So that is the question, and that is the question for Thursday. All right. Because we also have to go over the cross product next class, and then when we do that, I'll put it all together for you so it makes sense.
Oh, wait, cross product.
I put a star on it for you because I used my teacherly right of doing the easy one in class and leaving the terrifyingly hard one for you to do on your own.